This is the report for Lab 3. So for the introduction, basically what we're doing in this lab is using a smartphone magnetometer app, a bar magnet, and a meter stick to create a magnetic dipole. We begin by compensating for magnetic north by finding a spot where the x component of the magnetic field reads 0. Then we record and use experimental data and the Biot-Savart law to calculate the dipole moment of the bar magnet. And then we'll use this data to explore more complex models in GlowScript. So for the assumptions, my magnetometer readings fluctuated a whole lot, so my experimental values are an approximate of the display value. It displayed everything in microteslas, and the decimal component of this was changing constantly and never settled on a value, but for the most part they are right. My technical difficulties didn't allow for perfect compensation for magnetic north either, so because my x component usually fluctuated between negative 0.5 and positive 0.5 microteslas, and my GlowScript calculations were made based on the calculated dipole moment, which is not an exact value due to error in the experiment. And I also ignored external conditions such as the phone moving, electrical outlets, and other things like that. For example, it was a thunderstorm when I was doing this lab, so I couldn't go outside, and I also have cats that were doing zoomies around the house, and I noticed the magnet bumping several times, so that probably did impact my data a little bit. So the experiment, and I'm going to go into a ton of detail on this because I've already touched on it. Basically, we're using a magnetometer app and trying to compensate for external magnetic fields as much as possible. Then we record some on-axis values and some off-axis values to come up with a dipole moment to use in further calculations. And here's a picture of the off-axis procedure. You have your phone that you do parallel from the magnet at first, and then you move it north a little bit more to have that perpendicular section there. So for the data, here's what I got in Excel. On the left is all of the on-axis measurements that go into this graph here on the right, and at the bottom is the off-axis field measurements. And the key observations from this are that the ln of bx versus ln of r results in a trend line of y equals negative 2.9548x minus 13.743. The d in the off-axis measurements is approximately 0.301699 meters. By corrected is approximately 2.97667 times 10 to the negative fifth teslas, and the magnitude of B net is approximately 3.48534 times 10 to the negative fifth teslas. So for the initial calculations, you just go back over this equation from the trend line before, and you're looking for k. So you do your ln k, which is the y-intercept here, and you solve for k through that. And then you know that k equals mu 0 over 4 pi times 2 mu, and then you rearrange that to solve for mu and plug in your values. You get mu equals 5.376. This is the dipole moment of the bar magnet. And this on the right is percent error for n, which is the slope over there. We know that it's supposed to be negative 3, and if it's a totally different value, like if what we got is a totally different value, then we know that we've messed up in calculating the dipole moment. But my percent error is about 1.5%, which is pretty good, so we know that this is a reasonable value to use for further calculations. And now for the GlowScript program. So the objectives are to write a program that calculates the magnetic field produced by a dipole and use this model to compare the analytical results to experimental values. So here's the code. Up top we have the function for calculating the magnetic field made by a dipole, and then we set up observation locations needed for later calculations. We have some that are on axis and some that are off axis. Down here at the bottom is the on axis ones. I've pointed out the lines that create the arrow for the magnetic field at those observation locations, and these are going to be the light blue arrows in the output. And here we have basically the same thing as this last part, except these are the perpendicular ones, and these are going to be the purple arrows. And here we've input the experimental data, so I've got the d-perp value from my Excel sheet earlier. And then I've highlighted where this is going to be the pink arrow. This is the magnetic field on a 45-degree axis. And I added the magnitude of this magnetic field for error calculations that I'll use later to determine the validity of the experiment. And here's just a picture of the code output. There are more than 3 purple arrows. One of them is behind the really big one in the middle. You just can't see it in this. In error calculations, the percent error, my By corrected, I used my observed value is what I found in the experiment. My theoretical value is what was calculated in the GlowScript code, and I got a really small percent error, which is pretty good. My magnitude of B net is not as good. 12.6% isn't a super bad percent error. I noticed that my Z component was registering some value, and it's not supposed to register any value. It was 0 in the code, but it was around 3 microteslas, so that wouldn't be affecting it too much. I did have some issues with the X component being off, so that's probably where that came from, which means that I didn't completely account for the Earth's magnetic field. And sources of error, just kind of recapping from before, the Earth's magnetic field was accounted for in data collection, but it still may have affected the recorded values. External magnetic fields that weren't totally eliminated may have affected observations as well, and bumping the phone can impact results. I also did this experiment twice with 2 different apps and got totally different results the second time that were much more consistent, but it's still possible that those weren't perfect values. So for the conclusion, some final observations. How does the position of the magnet in relation to the magnetometer impact the X component measurement? So for this, what I did is I set it equal to 0. I found where the X component was 0, and then I introduced the magnet. And the closer the magnet got to the magnetometer, the more negative the value got. When the magnet was right next to the phone, the X component was around negative 3,000 microteslas. And what if you were to stick two identical magnets together end to end and run the experiment again? So the direction of the magnetic field would not change, but the magnitude of the dipole moment would double, so therefore the magnetic field would increase in magnitude as well. And what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? So without compensating for magnetic north, the magnetic end direction of all results will be impacted by the Earth's magnetic field. So you wouldn't really be able to be sure what exactly was because of the Earth and what was because of the magnet itself. So the experiment would be a lot more difficult to do accurately.